Hello students, welcome to Spectra Education Academy. In this video, I am going to explain answers for previous NEET question papers from the chapter Gravitation. The first question is the ratio of escape velocity at Earth. So V to the escape velocity of a planet. Radius whose radius and mean densities are twice as that of the Earth. So first let us try to get the escape velocity in terms of mean density and radius. So get back the formula of escape velocity, that is root 2 gm by r. So therefore this is going to be 2g density, mass you convert as density into volume of the sphere. So this is going to be 2g, rho will continue, 4 by 3 pi r cube. Volume of the sphere is 4 by 3 pi r cube divided by r. So one r gets cancelled. So you'll get escape velocity proportional to r without root, and in the root you have rho. So other term or other quantities are constant. So escape velocity on the earth, escape velocity on the planet. So it will be, this is r on the earth, this is r on the planet, into this is under root the density of the earth, mean density of the earth, mean density of the planet. So therefore they mention radius and mean densities are twice. So therefore for the earth you take radius, for the planet you take 2r because double under root. This is rho for the earth, this is 2 rho for the planet. This and this get cancelled, r and it get cancelled. So 1 by 2 root 2 is the answer. The last option is correct. Moving to the next question, question number 2. At what height from the surface of the earth the gravitational potential and the value of gr minus 5.4 into 10 to the power of 7 joule per kg and 6 meter per second square. Take the radius of the earth as 6400 kilometers. This is given in 16. So get back gravitational potential and gravitational potential formula minus g m by r plus h. So we are looking for h value. Then we have even g value also they mentioned. This value is given as minus 5.4 into 10 to the power of 7 joule per kg. Now this is gm by r square. In particular at a height h is h r plus h whole square. It is given 6. Now you call this the equation 1, you call this the equation 2, you divide them. Vg by g. So this is gravitational potential. So then gm by r plus h divided by gm by r plus h whole square. So gm get cancelled. 1 r plus h get cancelled. So it will be r plus h. So therefore Vg is 5.4. So you can cancel minus both sides. So Vg is 5.4 only. 10 to the power of 7. Then g is going to be 6 is equal to r plus h. Now, so this is 0.9. You can make this as 9 into 10 to the power of 6 or 1000 kilometers is equal to r dimension 6400 kilometers plus h. So 9000 minus 6400. So it will be 2600 kilometers. This is the answer. So third option is correct. Moving to the next question, question number 3. A satellite of mass m is orbiting the Earth, radius r at a height h from its surface. The total energy of the satellite is g0. Total energy of the satellite in terms of g0. So we have to find out total energy only. The value of acceleration due to gravity at the surface of the. So total energy is, you understand, like total energy for the satellite it possesses kinetic energy due to its orbital velocity, and get back the expression of potential energy. It is gmm by r plus h. So orbital velocity when satellite revolves at a height r plus h from the center. So m, get back orbital velocity. It is orbital velocity at a height is gm by r plus h. So when you square it, root get cancelled. So this is going to be r plus h only minus gmm by r plus h. So LCM will be 2 of r plus h. Then this is going to be just gmm. This is minus 2 gmm. So this is minus gmm by 2 of r plus h. So, but you have to express in terms of small g. So get back the relation small g and capital G are related like this. So this is going to be gm has to be replaced with the gr square. So place gm as gr square, g naught r square in particular, with m divided by 2 of r plus h. So second option is correct. Moving to the next question. This is related to the graph. Starting from the center of the arc, having radius capital R, the variation of G is. So G is almost numerically equal to gravitational field. Let me show. G is equal to Gm by R square. Let me also show gravitational field intensity due to a mass of 1 kg. So because when 1 kg is kept in the gravitational field due to another mass, so the 1 kg mass get influenced. So that is the idea of gravitational field intensity, force per unit mass. Force experienced by unit mass placed at a point in the field is nothing but gravitational field. Therefore, when after you place 1 kg mass, it experiences gravitational force. So it is Gm into 1 kg by r square divided by the semi is also 1 kg. It cancels. So therefore, acceleration due to gravity is numerically equal to gravitational field intensity. Yeah. For the case of a sphere, we get the formula Gm into small r inside the center of the arc. So at a distance r which is less than radius of the sphere. So this is the expression. It is going to be r cube. So therefore, till the top of the sphere, E proportional to r. It means G proportional to r. Once, if r is greater than capital R, so we write the equation outside. This is well outside, or at least on the surface. If you take r is equal to r, thereafter, so E is equal to Gm, r is capital R divided by r cube. So therefore r square. So thereafter, if you take any point, any place outside, it will be E is equal to Gm by small r square. So therefore, first increases. E proportional to r means what? As E increases means G increases. As r increases, G increases, because E numerically equal to G. So as r increases, G increases. So therefore, thereafter, inversely proportional to r. So second option is correct. Now moving to the next question. Two astronauts are floating in gravitational free space after having lost contact with their spaceship. The two will. So they attract each other, they move towards each other. Yeah, so because it is gravitational free space. Yeah. Next, moving to the acceleration due to gravity. So they are moving in a gravity free region. Gravitational free region means this part does not exist. F is equal to gmm by r square does not exist. So therefore, only the weight part will exist. Yeah. So acceleration due to gravity may be present, due to which they both get attracted towards each other. Next, moving to question number 6. The acceleration due to gravity at a height 1 kilometer above the earth, at a height 1 kilometer above the earth is equal to at a depth d. So therefore GD. So get back the formula GH. So GH is 1 minus 2h by r. Then next G value at a depth d. So G of 1 minus d by r. So G and G get cancelled. Height is given 1. And okay. Acceleration due to gravity at a height is equal to, at a height 1 kilometer. So therefore 1 minus 2h by r is equal to 1 minus g by r. Therefore 1 and 1 get cancelled. Yeah, this r and r get cancelled. Therefore d is equal to 2h. H is like mentioned 1 kilometer. So it is 2 kilometers. This is the answer. The third option is correct. Moving to the next question. This is based on Kepler laws. The kinetic energy of a planet in an elliptical orbit about the sun at positions A, B, C, KA, KB, KC, respectively. AC is the major axis, SB is perpendicular to AC at the position of the sun as shown in the figure. Then, so remember, semi-major axis is AC, semi-minor axis is entire B and crossing S up to here. So kinetic energy at A, because it is closer to the planet, kinetic energy is at E. Angular momentum remains constant only. Kinetic energy is involved with half mv square. So therefore, when you talk about angular momentum constant at any position, you can say m1 v1 r1 is equal to m2 v2 r2. So therefore, mass in same planet only. If less is r, more is the speed. So therefore, A is closer, poses more kinetic energy. Somehow B is farther, so therefore less kinetic energy. So this is KEB is equal to half MVB square. So therefore, V is at a distance in the middle, B is at a distance in the middle. So therefore, next case is second. Third case is it is farther. So therefore, KE at E, kinetic energy at E greater than kinetic energy at B greater than kinetic energy at C. So therefore, this is farthest point. If R increases, V decreases. So kinetic energy decreases. So second option is correct. Moving to question number 8. If the mass of the sun were 10 times small and the universal gravitational constant were 10 times larger in magnitude, mass is 10 times smaller and universal gravitational constant 10 times larger in magnitude. Which of the following is not correct? So raindrops means, to get back the formula, G is equal to Gm by r square. So this is mass of the sun, this is gravitational constant. You don't have mass of the small body. So raindrops are considered a small body independent of mass. You don't have mass here. Walking on the ground, yes. So this is related to small only, small m only. So therefore, there is no m in the equation. Then time period of the simple pendulum. So time period of the simple pendulum also is not associated with the mass of the bob. You have only L by G. So there is no relation to the particular question. So yes, definitely when this mass and this G changes actually, but they mentioned in the question will not change. So this is wrong. So fourth option is correct. Students, in my next video, I'll continue the answers for the remaining questions in the same chapter. Thank you very much for watching my video, but don't forget to share and subscribe with your friends and relatives.